Hello. In this section, we are going to introduce the idea of probability distributions. A probability distribution models the possible outcomes of a random experiment. Oh, a random experiment. Oops. All right, so let's look at an example to just orient ourselves. Let's say that we are looking at a playlist that has 10 songs on it. Six of the songs are rock. Two are country. One is hip hop. And one is opera. What is the probability distribution for a randomly selected song to be rock? And so what you want to do is you want to go through and construct all the possible outcomes. So what are the possible outcomes for a song to be rock? The way that we can present it in a table. This table is way bigger than we need, but it's fine. What are all the possible outcomes? Well, if we're asking for the song, whether the song is a rock song, then one outcome would be that the song is a rock song, and the other would be that it's not. And then over here, what we want to do is we want to put the probabilities. So assuming these are equally likely outcomes, what you can do is you can go through and construct the probability by looking at the number of things that are in the event space versus the things that are in the sample space. So there are, for a song to be a rock song, there are 6 possible ways we could get a rock song. And then there are 10 things total in the sample space. Not a rock song, there are 4 possible ways we could get not a rock song out of 10 total things in the sample space. And one of the things to note is that these add up to 1. That should always happen because you want to represent all the possible outcomes. Okay, and so that's an example of a probability distribution. So we have a probability of all the different outcomes of our randomly selected song. Okay, so next we're going to kind of change gears briefly, and that is we're going to discuss the idea of discrete versus continuous variables. Now, the reason that we're going to do this is because when we look to model probability distributions, we're going to end up using different structures for doing that, depending upon whether the data is discrete or continuous. Let's start off by talking about discrete data. So discrete data is countable. We'll talk about what that means in a minute. So it's countable, or it can be listed. Over a defined range. So let me briefly talk about what we mean by a defined range. So you have kind of bookends for the numbers. So if you have from 0 to 5, right? So discrete data would be, you'd have a countable number of outcomes that are between 0 and 5. So, and countable, that word just seems weird. So countable just means that you could go through and on a piece of paper, you could just write all the possibilities down. So what would be examples of like countable numbers between 0 and 5? Well, you could have 0, 1, 2, 3, 4, 5. You could write, because you can write those down. You could write down 0 through 5. You know, and so you've got some random experiment you're doing, and the outcomes are from 0 to 5. If that's the case, then that's just that data is discrete. Okay. Does it have to be in whole number increments? No. You could have 0, 0.5, 1, 1.5, 2. So you could, you know, again, that's a listable number of possibilities. You can write all the possibilities down. You could get out a piece of paper and you could just write them down. If you could write out or list out all of the possibilities over a defined range, then that's discrete data. Another way of looking at it is that discrete data has finite possibilities. Over the range. The word finite there effectively means the same thing as countable or listable. You can actually go through and have a, now finite can be a lot of possibilities. So from 0 to 5, you could have a lot of possibilities. If you went through and listed all the possibilities and they were by let's say they were by 0.1. So you'd have 0, 0.1, 0.2, 0.3, 0.4, 0.5, and you just kept going, adding each time 0.1 until you got to 5. You'd have a lot of outcomes to whatever experiment you're doing, a lot, right? But you'd still have a finite number. You'd have 50 outcomes. You'd still have a finite number. 50 things, you can write 50 things down. So if you can write out all the outcomes over a range, then that means the data is discrete. And then the example textbook gives is phone numbers. There are a lot of phone numbers out there, a lot. But if you were patient, you could sit down and you could write out all of them. It would take a very, very, very long time. It'd be easier for a computer to do it, but a computer could literally go through and list all the possible phone numbers in existence. There are a finite number of them. They can be listed, they can be counted. All right, so let's compare that now with continuous data. Continuous data is not countable. Or it cannot be listed. There are infinite possible outcomes. Over the range. And what are examples? So essentially, the continuous data is something where you could always add more decimal points. You could always get smaller increments as many times as you want. So examples of things where you can do that are things like measurements, like a weight or a height. Or time. So in terms of weight, right? So let's say you went through and you weighed yourself and you weighed 140 pounds. Or actually, sorry, this is supposed to be in terms of experiments. Let's say we were going through and we were doing an experiment and we wanted to model possible outcomes, and the weight ranges were from 120 to 180 pounds. Okay, and so let's say, so you want to go through and list all of the possible outcomes from 120 to 180 pounds. Is that possible? The answer is no, it's not possible to list all the outcomes. Why not? Why can't you list all the possible outcomes for weights? Why couldn't you go through and say, all right, well, someone weighs 120, or they weigh 121, or they weigh 122 pounds, or they weigh even 120, 120.1 pounds, 120.2 pounds, 120.3. Can't you go through and have and just use, if you use a small enough decimal increment, can't you go through and list all the possible outcomes? And the answer is no, because you could always add more decimals. So if you said that, okay, I'm going to go through and I'm going to list all the possible outcomes, and I'm going to do them by 0.1. So I'm going to do 120, 120.1, 120.2, 120.3. I'm going to do that all the way to 180 pounds. That's all the possible outcomes. And then I come up to you and I say, well, my weight is 151.37654.2.1, or 1 pounds. Okay, so I go through and I give you, 7 decimal points worth of accuracy on my weight, and then suddenly it breaks your 0.1 increments, and so you're like, okay, well, let's do 7 decimal points worth of accuracy on weights, and then someone comes with 14 decimal points worth. You can always add more decimal points to weights, and the same thing is true of heights or times. Okay, so anything where you can always add more decimal points of accuracy, that's going to be examples of continuous, an example of a continuous data thing. And so that's the way to think about it, is that discrete has a limited number of possibilities, like phone numbers. With phone numbers, we don't add decimal points. You don't have, your phone number, I was going to give an example. What's an example of a phone number? 555 5555. We don't go through and then add a 0.5, or a 0.55, onto the end of a phone number. There are a finite number of possibilities with phone numbers. And so anyway, that's the difference between them. So that's the way you want to think about is, are there finite possibilities? Is there a limited number of possible outcomes? Could you go through and count them or write them down, even if there were a lot? If so, then that's discrete. If it's not countable, can't be listed, infinite outcomes, you can always add more decimal points to get even more accurate, then that's continuous. That's the difference between the two. If you're listening and you're a little bit, you're a little bit fuzzy on it, I remember learning about this and thinking that the difference is a little bit a little esoteric. It's a little bit hard to understand, but you just got to work with it. And I do think it's possible to understand the differences here. You just got to work on it. We will go through and look at some examples, but I don't know if the examples are necessarily going to be, well, I don't know. Maybe it will make perfect sense to everybody. I remember learning about this and thinking that it was a little bit difficult to understand. All right, so we're going to put some experiments here, so that where we want to go through and model the outcomes, and the question is, are these discrete or continuous? When you were going to go ahead and put together your probability distribution, which you'd have to do something different for each. All right, so you're going through your random experiment is to model the weight of submarine sandwiches. You go to a delicatessen and they are making submarine sandwiches, and you're going to go through and you're going to weigh them. All right, so think about that. Is that continuous or is it discrete? All right, you have another experiment. You have the elapsed time from home to class. So you're collecting that data for the entire classroom, and you're going to go through and model the possible outcomes for that, the elapsed time from home to class. Is that continuous or discrete? The number of people in a passing car. You're on a road trip and you're collecting data on the number of people that are in passing cars, and you're going to go through, and at the end you're going to represent the results using a probability distribution. Is that discrete or continuous in terms of the data? The blood alcohol level. Of drivers. So this experiment might be done by the police. The police are stopping people and having them, blow on a breathalyzer, and they're recording all of the blood alcohol results, and they're going to represent that results with a probability distribution at the end. Is that continuous or discrete? The number of eggs laid by salmon. I don't know how you'd collect that data, but the idea is that you have salmon, they're laying eggs, you're going through and you're modeling the probability distribution for the number of eggs that are laid by the salmon. So you're counting up how many eggs are laid and using that to represent the salmon. So, all right, so while I listed this, you had a chance to think about it. Are they continuous or are they discrete? Weights of submarine sandwiches, that is continuous. Weights are continuous. And the reason is that there are infinite possibilities between any weight range. And that means any weight range. You could have the weight range for submarine sandwiches could be from 0 to 1 pound. And that's our defined range. So well, I guess a sandwich is not going to weigh 0 pounds, but anyway, you get the idea. You have a bottom, the lightest sandwich to the heaviest sandwich. Maybe there's only a pound. Well, pound maybe seems like a lot. Anyway, there's a difference between the lightest and the heaviest sandwich, and there's infinite possibilities between that range because weights are always infinite. No matter what the defined range in weights are, you can always add more decimal places and get even more accurate when it comes to going through and measuring the weight. And so that's an example of continuous data. The elapsed time from home to class, that's also continuous. Times are continuous. You can always go through and add more seconds or tenths of seconds or hundredths of seconds or 10,000ths of seconds to go through and get even more accuracy, even a smaller difference between times, when it comes to go through and measuring accuracy. And so because of that, it's continuous. The number of people in passing cars. We don't have half people or quarter people or decimal points of people. You can't break up people into smaller pieces. And so because of that, the number of people is going to be discrete, right? So the number of people in passing cars, so you could have, obviously the smallest would be 1, assuming you're not talking about autonomous vehicles. So the number of people in a passing car, the smallest is going to be 1. And then if you had a really large, bus, maybe that bus could hold 50 people or something like that. But if you went through and listed the possible outcomes from 1 to 50, you could list all of them. There's 1 person or 2 people or 3 people, all the way down to 50 people. If you can list all the outcomes, that's discrete. The blood alcohol level. So blood alcohol levels are measured. You could add more and more decimal points to get even more and more accurate. And so there's an infinite amount of possibilities for blood alcohol levels between any given range. I'm not that familiar with blood alcohol levels, so I don't know what a reasonable range is, but that's continuous data. And then the number of eggs that are laid by salmon, I don't know how many I have no idea how many eggs salmon lay, but even if they laid thousands of eggs, thousands of things can still be counted. You don't have half eggs or quarter eggs or decimal points of eggs. And so because of that, it's discrete. Might take a while, but you could list all the possible number of eggs that salmons could lay. Okay, so now that that's out of the way, what we're going to look at is we're going to look at the 2 different types of distributions we can do for the 2 different types of data. So discrete probability distributions are first. So they typically are represented using tables or graphs. Right, and we want to list all the possible outcomes. Right, and so because discrete data is listable, we should be able to list all the possible outcomes and show the probability of them. Let's look at some examples. Suppose a stats class is 60%, or sorry, 40% male and 60% female. If a person is randomly selected, what's the probability that they're female? All right, and so we could do that with a table. And what we want to do is we want to do outcomes and probability. So one outcome would be, and so and this example is done using coding. So one outcome would be 0, which would represent false, and the other outcome would be 1, which would represent true. So actually, let me do this instead. So we are listing the possible outcomes here, but we're going to label it with female so that the coding makes sense. All right, so false, true. If you get a false for female, that means that's male. So the probability would be 0.4. And for true, the probability would be 0.6. And notice the sum is 1. That should always happen. And so those are the only 2 outcomes. If you randomly select a person, the person's either going to be male or they're going to be female. We can also graph that. And so when you construct your graph, you'd want to go through and have 0, 1. So we're graphing the possible outcomes. So 0, we'll do 0.2, 0.4, 0.6. So with 0, 0, we get a 0.4 probability. So you go through and just do a little graph like that. Actually, you know what I could do? I could use the line tool for this. Oh, that's a little off. All right, anyway, and then for 1, you get 0.6. And there's the graph, and that's the probability distribution. So here is in a table, and here is in a graph. All right, let's go through and try an example where we have more than 2 outcomes, because we actually have already looked at the first example that we did at the beginning of the lecture was also discrete. Let's look at a discrete outcome where we have more than 2. All right, so Amazon has a rating system where you can go through and review products. Their customers can review products. All right, so suppose we go through and look at the review results for a product. And what we want to do is we want to go through and select a random review. What's the probability distribution for the outcome? All right, so the Amazon system, I don't think that they have half stars. I think that they only have full stars. And so this is definitely discrete data. There is not an infinite number of possibilities. You can't go through and give products a 4.57643 review. You can only give 1, 2, 3, 4, 5. Okay. And so we're going to put all the different, we can list the possibilities. So we'll have number of stars. And then we'll have the probability over here. So you'd have to go through and calculate this by hand. I'm just going to end up giving you this information because it's actually not given in the text. But the idea is that you could have 5 stars, 4 stars, 3 stars, 2 stars, and 1 star. And let's say you go through and the way to calculate the probability here, if you had the actual data, is you count up the number of 5 stars and divide by the total number of reviews. So you count up how many 5 stars are there over how many total reviews are there, and that's going to be the probability of getting a 5 star. That's the number of things in the event space over the number of total things in the sample space. All right, and so we're just told that that's 0.44. 4 stars, we get 0.15. 3 stars, we get 0.10. 2 stars, we get 0.11. And 1 star, we get 0.20. All right, so we've got this is our this is our probability distribution. It's the distribution of all the probabilities. Okay. And then once you've got that, you can go through and you can graph that. So we could do 1, 2, 3, 4, and 5. And so we do want to have up to at least 0.44. So you'd want to do 1, 2, 3, 4, 5, I guess. So we'll say 0.1, 0.2, 0.3, 4, 0.5. 1 star, we get, that's about there. 2 stars, it looks as around 0.11. 3 is right on 0.11. Wait, what did I say? So yeah, 0.11, 0.1, and then 4 is 0.15. So it's going to be halfway between these, maybe about there. And then 5 is 0.44. So it's going to be about halfway between these. And then we can put little lines up to these. This. And that's the graph of all the possibilities. Right. So we've got all the possible outcomes. There are only 5 of them. There's a listable number. So thus it's discrete data. And then we can put the probability of each of the outcomes, and then we can go through and plot them. All right, so one more discrete example. So discrete distributions can be described using equations. This is also going to give a discrete result that is infinite. And so I think it's an important kind of exception to the rule. All right, so suppose we're modeling a couple having children. And they want to have children until they have a girl. What's the probability distribution for the number of children they would need to have? So we're going to assume that the probability of having a girl is 50%. So we can use a table to list the possible outcomes. This is where things are going to get a little weird. There are actually infinite outcomes to this. It is possible. It's possible, not likely, but it's possible to keep having children forever and never have a girl. That's possible. It's not very likely. So over here, we're going to have number of children. And then we'll have the probability. All right, so if you have one child, what's the probability that the child is a girl? 1/2, 50%. If you have 2 children, what's the probability that that you have a girl? Hold on. Okay, I wanted to make sure that I explained this correctly. So the idea is that you have a girl, and so we're finding that the probability that you have 2 children where the first is not a girl, but the second one is. So if you go boy, then girl, then there's a 1/4 chance of that. All right. If you have 3 children and you had to have 3 children before you got a girl, that means you went boy, boy, girl. The probability of going boy, boy, girl is 1 in 8. What about 4 children? Again, you're having children until you get a girl. So what's the probability that you go boy, 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 girl? That's going to be 1 in 16. Well, that 1 in 16 chance that happens, but it could happen. What about 5 children? 1 in 32. You guys see the pattern hopefully here. 6 children, 1 in 64. This could go on forever, for infinite. So there's actually infinite outcomes here, but it's still finite data in that it's not infinite over a defined range. There is no defined range. You could have an infinite number of children. And so what you can do here is you can go through and represent this as a formula where you have X number of children, and the probability that you have to have X number of children before you have a girl is 2 to the X. Okay, and so we could go through and create a formula for this to represent it. Okay, and so I guess I just want to pause here because this is an exception to the rule where there are infinite outcomes, but they are the infinite outcomes are not in a defined range. So that's why the defined range part is in the definition for discrete versus continuous, in that the defined range is critical to going through and determining the difference between them. With discrete data, you can have outcomes that go on forever like this. This is discrete data in that you're not going to have half children or quarter children or tenths of children or 1.75432 children. This is discrete data in that it is kind of in a way it's countable, even though it's countable that it goes on forever. And so it's an important exception to the rule in that if you don't have a defined range, then you can have an infinite number of outcomes and still have the outcomes be discrete. And then you can go through and graph this. It's just your graph is going to go on forever. So if we went through and put 1, 2, 3, 4, right, and then it's just going to end up going on forever. And then our outcomes, we just do half each time. So we'll say that our largest number is 1/2. So we'll say this is 1/2, and we'll go ahead and put a dot for that. And then 2 is going to be half that. So it's right about there. And then half that, and then half that. And it just does that forever. Okay. And then we can go through and put our little lines on here. All right, let's talk about continuous. So continuous probabilities are represented using area under a curve. Kind of giggled there because I distinctly remember when I learned this the first time. This is a very strange thing. Discrete distributions, discrete probabilities may seem weird until you look at continuous probabilities. All right, so why do we end up doing it this way? The reason that we're going to end up using this area under a curve idea is because it's not possible to list all the outcomes. So because of that, we need to do something clever. And so that's what we're going to do. So because of that, we can go through and we can give, when we're going through and doing probabilities, we can give a range of outcomes. But you can't go through, and if you have continuous data, so this is one of the things that's going to be a little strange, is you can't go through, and let's say let's go back to the weight example. So you have 120 to 180 pounds. Let's say you measure the weights of people in class, and they weigh from 120 to 180 pounds, and you want to find the probability that someone weighs exactly 140 pounds. The probability of someone weighing exactly 140 pounds is going to be 0. And the reason is that if you think about, if there are infinite outcomes between 120 and 180, then each individual outcome in there, it has infinitesimally small amount of probability. And so because of that, what we're going to do is, instead of measuring probabilities of any given outcome, which is again, with an infinite number of outcomes, is going to be infinitesimal. What we're going to do is we're going to measure the probability that someone has, instead of doing 140 pounds, we can measure the probability that someone has that weighs between 139 and 141 pounds. And by having a range of outcomes, then we can go through and find out how much how much space that range takes up out of the total amount of space between 120 and 180 pounds. And that's going to be the idea of the area under the curve. So because we cannot list all the outcomes, we're going to have to look at ranges of outcomes. I want to be specific there, because it's not possible to list all the outcomes. And then, so it's just a quick example here. So suppose we are looking at wait times at a coffee shop. What we would look at is the probability that someone has a range of times for how long they would have to wait, such as, for example, less than 2 minutes. All right, so let's look at an example of a continuous probability distribution. So this is what our probability distributions are going to look like. They're going to look like a graph. And we're going to go through, and this is modeling the wait times at a coffee shop. And so what we're going to do is, again, because if someone said, what's the probability that your wait time is exactly 1 minute, the probability of your wait time being exactly 1 minute is 0. And the reason for that is because every number of possible outcomes from, zero, in this case, from 0 to 5 minutes, there's an infinite number of them. And so it's infinitesimal. And you say, wait, no, but the probability of exactly 1 minute is, it can't be infinitesimal. And again, it's because you're not thinking of terms of, we're talking about exactly 1 minute, like 1.000000000, infinite number of zeros minutes. We're not talking about 1.01 minute. We're not talking about 1 minute and a billionth of a second. We're talking about 1 minute exactly with an infinite number of zeros behind it. The probability of that is 0 because there are infinite outcomes. And so because of that flaw, or that issue, right, where we could just keep adding more decimals. What we need to do is we need to have ranges of possibilities. And so what we can do is we can go through and have from zero, from 0 minutes, the idea is you walk right up and you immediately get your order completed, to 2 minutes, and we can go to this. And when we say it ends at 2 minutes, we mean 2.0 and infinite zeros of minutes, infinite zeros of accuracy there. And so because we could go through and do that, now between those two things, there is going to be outcomes. There is going to be data between those. So while the outcome being exactly 2 minutes, the probability is 0. The outcome being from 0 to 2 minutes, there's a lot of outcomes that meet that criteria. If your wait time is 1 minute, that is between 0 and 2 minutes. If your wait time is 1.00001 minute, that is between 0 and 2 minutes. All right, and so by going through and doing ranges of values, that enables us to overcome the problem of infinite outcomes of the continuous data. And so what this curve represents is it represents this is really esoteric, but it represents the density of outcomes. And so by using the density of outcomes, we can go through and count up how much space those outcomes make out of the total possibility and use that to calculate the probability. So if we, for example, let's just say, for example, if you went through and this curve gave you again, this is like the idea of density is how many outcomes there are for that waiting time. If we took the total curve and we said the total curve, which represents the maximum amount of possible wait times, all the possibilities together have to add up to 1. So let's say the total curve is 1. Total area under curve is 1. Okay, and again, the reason for that is that if this curve represents all the possible outcomes, and we sum up the probability of all those outcomes, just like with the discrete results, we should end up getting them to sum to 1. And so the total area under the curve would be 1. And if we went through and said, all right, well, if the total area under the curve is 1, and then the area under the curve that's shaded here, which represents all the outcomes that have between 0 and 2 minutes, let's say that total area, I know it's hard to eyeball, looks like about half. Let's say that total area is 0.5. Then we can say that the probability that your wait time is from 0 to 2 minutes is 0.5. It's the portion of the whole for all. It's the portion of the outcomes that represent that range. It's the portion of all the possible outcomes over the total outcomes. So 0.5 out of 1, or 50%. All right, so yeah, that's our example. There's nothing else to say about it other than what I just said. All right, so let's go and do an example. So this would be, okay, I guess there is one more thing to say, and that is in terms of calculating this, if you were looking at this, you could try and eyeball it, which is what I just did. If you were going to go through and do an estimate, you could estimate it, but that's not what we're going to do in future sections. In future sections, the calculation for what we just did, trying to find the total area, a computer is going to do that for you. So the computer will go through and calculate the amount of area that's under the curve. So we will use tools to go through and calculate it, but it's important that you understand what the tools are doing. All right, but just to kind of illustrate what those tools are going to do, let's look at an example where we could go through and do the probability by hand. Hopefully it will help to give something concrete that you can kind of wrap your arms around, because it's definitely a weird idea. I don't want to give you the the impression that this makes. I think the way you handle discrete probability distributions is really quite logical and rational, and it's one of those things that you see it and you're like, oh yeah, of course that's the way that you do it. But then you get to continuous, and you're like, wait, what area? Yes, that's how it works. All right, so suppose a bus arrives every 2 minutes to a pickup stop. If a person arrives at the bus stop at a random time, what's the probability distribution for how long they'll have to wait? Okay, and so the way that we represent, so this is continuous data, right? So when it comes to all the different possibilities, you can go through and have an infinite amount of accuracy when it comes to wait times. And so again, the probability that you'd, why did I put 2 minutes? It's supposed to be 12 minutes. So the probability that you'd wait exactly 2 minutes on the dot, 2.000000 minutes, the probability of that's 0. So this is continuous data. However, it's very simple data, and so you can go through and graph this. Now, I'm not saying that you'd think to graph it this way, but when you see it, you can actually. So potentially you could wait 0 minutes. You could walk right up and immediately get on the bus, or you could wait 12 minutes. So the bus leaves just as you're walking up. Now, if you're arriving at a random time, then the probability of any given time, they're all the same. All right, so you're going to have the same height bar all the way across the top here. Every single outcome is equally likely. Like no outcome is more likely than another if you arrive at a random time. And so our probability distribution in terms of our graph looks like this. Okay, and so because of that, to go through and find the height here, since the area under the curve, the total area needs to be 1. So it needs to be 1 because all the possible probabilities need to add up to 1. That means that this needs to be 1/12. Why is that? It's just if you take the area for a rectangle is base times height. If we have to have base, which we can see here is 12. If 12 times something needs to be 1, then that something needs to be 1/12. Okay, so this is what our graph looks like. And now you can go through and we can calculate probabilities by finding portions of the area that's underneath this. So let's say we wanted to go through and find the probability that someone will have to wait between 4 and 10 minutes. All right, so to go through and calculate the probability that someone waits between 4 and 10 minutes, what we need to do is we need to go through and put 4 on here, put, I don't know, I'm just eyeballing this, put 10 on there. So there's 4. Now we're talking about 4.0000000000 forever minutes up to 10.000000 forever minutes, like exactly on the nose, 10 minutes. All right, and we want to go through and find the to find the probability that you wait between 4 and 10 minutes. We want to find the portion of the graph here that's represented by that region. And so we just want to go through and find the area for that. What would that be? So we could go through, that's also a rectangle. And so you could do area equals, base times height. What's the length of the base? All right, well, the length of the base from 4 to 10, that's 6. What's the height for that rectangle? That's this value here, that's 1/12. And we get 1/2, or 50%. So that's an example that you could actually do by hand, calculating a probability with a continuous distribution using an area. It's a weird idea, but it can be done. But again, in future sections, we're going to have more complicated data than this. We're going to have data that looks more like the coffee shop where you're going to have a curve, but then a computer will go through and find the area that's underneath the curve to calculate the probability. However, in terms of explanations in future sections, things are going to be explained using the area under the curve idea. So you do need to understand, what's taking place, like why it's being done that way. Okay, so that's the idea. That concludes the video. Thank you for watching. See you next time.